Okay, a lot of people have been asking me in class, what's the difference between electric potential and electric potential energy? So in this video, I'm going to show you with simple examples what that difference is. So let's consider this situation like this. We've got two plates. One is positively charged at 5 volts, and you see it's got lots of positive charges on it. The other's at negative 5 volts, and it's got lots of negative charges on it. This has got positive Q. This has got exactly the same amount of charge on it, but of the opposite sign, okay? And now we want to talk about what's the potential of these two different plates. Well, let's see if we can plot that out. And we're going to do it with a graph that looks something like this. So down here, we're going to have potential. So potential is given in volts. It goes from positive 5 to 0 to minus 5. And then here's the position as we move from the left to the right between one plate and the other. Let's see how this should go. And right now, you should start to think about how you would plot it out. Okay, let me show you how I plotted it out. So I think it looks like this. Well, actually, I know it looks like this. So what happens is this plate, as I told you on the left, is at 5 volts. So here, I put it right here. So that's 5 volts there. And I know that this plate on the right is at negative 5 volts. So that's at negative 5 volts. So I put it as a little dot right there. And I know that the field basically is constant between these two plates. The electric field between two very large plates will be constant all the way through, independent of distance. But that doesn't mean that the potential is going to be constant all the way through. The potential is higher on the left and lower on the right. And so what that means is there's going to be a change in the potential as you go from one spot to the next. And so what happens is I'm going to be at high potential on the left. I'm going to go to low potential on the right. So I basically got to go through the origin. I've got to come to some point of 0 potential, which would be right about in the middle. And then I'm going to continue to increase in negative potential as I go further and further toward the negative plate. So the plot of potential versus distance looks like this. It's just a line going down like that. And what we can now think about is putting charges on this potential at various locations. And we can talk about what their electric potential will be. And after that, what I'll do is talk about moving charges from one spot to another. And then we'll talk about what their electric potential energy is. So first we're going to place charges. So imagine we've got two charges. One is a positive 1 coulomb in red, and the other is a negative 1 coulomb in green. I hope it's green. I'm colorblind, so leave in the comments below if I got it wrong. Don't mess with me. Be honest. Okay, so now what I'm going to do is I'm going to place these charges somewhere, and imagine that each one is just 1 coulomb, positive or negative. Okay, so now I've placed one of the charges. I placed the positive charge here at the minus 5 volt plate location. Okay, what is this electric potential? What's the electric potential in this situation? Well, the electric potential is just the voltage that it's at. So right here, it's just minus 5 volts. That's all it is. It's just the location of where this point is. Okay, so that charge is right there. It's at minus 5 volts. That would be at the negative plate. Okay, so that's all we have there. Let's do another one. Okay, let's see if this throws you off. This one is a negative charge. And I want to know what the electric potential is. So that's the voltage of minus Q. Okay, so the voltage of minus Q is, again, just minus 5 volts. It's just this location. When we say, what is the electric potential, in a way, we're asking, what is its height? Is it up high at 5 volts or is it down low at minus 5 volts? Okay, so hopefully you got this, but let's just do it one more time or 2 more times just to be sure. Now here, I'm taking the positive Q charge and I'm putting it up here on the positive 5 volt plate. What is the potential of this positive Q? It's just plus 5 volts because that's where it is. That's its height. So that's its electric potential. And here's the other one. Let's say I take the negative charge, negative Q, and I put it up here on the 5 volt plate. What is its electric potential? Well, it's just positive 5 volts. And again, the electric potential is just the height. That's all. Okay, now we get into electric potential energy, which occurs when we move charges in a potential. So let's take a look at this. Imagine I take that positive Q charge, okay? So let's just look at, this. I don't want to show the equations yet, but let's look at this charge down here. So it's a positive Q charge. I'm starting it at position A, and I'm going to finish up at position B. So I'm going to move it from minus 5 volts up to plus 5 volts, okay? So in general, the way that we calculate the electric potential energy is by saying, what is the change in voltage between point A and B? And then we multiply it by the charge, being careful to include the sign. And then that, V times Q, will basically be the electric potential energy. So I'm going to take this charge, the positive charge, at the negative 5-volt plate, and I'm going to move it to the positive 5-volt plate. Now, anytime we talk about a change in potential from point A to point B, we have to have a difference between the voltage at A and the voltage at B. But the rule we have in physics is always to take the second member of that difference and put it first. So if I want to know what the difference in voltage is between A and B, I take VB minus VA. Just like when we talked about in Physics 201, we said, I move from position x1 to x2. What is my displacement? My displacement is x2 minus x1. That's why it's voltage at B minus voltage at A. Well, what's the voltage at B? Voltage at B is positive 5 volts, okay? Minus the voltage at A. The voltage at A is down here, so that's minus 5 volts. So it's plus 5 volts minus a minus 5 volts. That's double negative, okay? So plus 5 volts minus minus is going to be plus 10 volts. And now I multiply that by the charge. The charge is positive 1 coulomb, and so I get 10 volts, 1 coulomb. That's 10 joules, okay? So the electric potential energy of this positive charge resting on the minus 5 volt plate is plus 10 joules. That's its electric potential energy. Now, another way to look at this is just to say, go back to the plate diagram and think of it this way. I took that charge, the positive Q charge, and I started out with it here on the negative plate. Now, since it's a positive charge and it's close to a negative plate, it is attracted to that plate, or as we say in class often colloquially, it wants to be on that plate because opposites attract. And now as I move it this way, if I move it all the way over to the positive plate, well, hey, it's a positive charge. It doesn't want to go to the positive plate. In other words, I need to do work to get it there. So moving it, pulling it off of this negative plate and pushing it onto this positive plate, that takes a lot of work. So that work is represented by the increase in its potential energy. Its increase in electric potential energy is 10 joules. So it takes 10 joules of work to lift it from this negative potential and put it to that positive potential. A way to think of this would be to take a heavy weight and lift it from the ground, which might be at point 0, up 10 meters. It might take you a lot of energy to take some 10 kilogram mass and lift it from 0 and put it all the way up to 10 meters. That's equivalently, analogously what we're doing here with this charge, okay? So you increase the electric potential energy. Let's do another example. So what if we take that charge and we move it in the opposite direction, okay? We're going to start out with this charge up at 5 volts, and we're going to move it down to negative 5 volts, okay? And again, the electric potential energy is given as the difference between the voltages between A and B times the charge, being careful to keep track of its sign. And so what I need to do is I say, okay, the second place I land is B, and the first place I started out is A, so it's got to be VB minus VA, okay? VB minus VA, okay? What's the potential at B? Potential at B is minus 5 volts minus the potential at A, which is plus 5 volts, okay? So that's minus 5 volts minus 5 volts, that's minus 10 volts. So I take minus 10 volts, I multiply it by the charge, keeping track of the sign, it's plus. So negative times a positive is going to be negative 10 joules. So the potential energy is negative. What does that mean? That means I gave up potential energy when I moved the charge from point A to point B in this scenario. What would that look like in terms of the plates? Well, let's go back to that. That's the equivalent of doing this. I take this charge, this positive charge that is near the positive plate, and believe me, it doesn't like being there in a sense, as we colloquially say it. What happens is the positive charge is repelled by the positive plate, and so it would naturally, if I just let it go, it's going to go this way, and it's attracted to the negative plate. So if I hold the charge there, it's got potential energy, but once I let it go, it's going to just naturally, in a sense, fall down to the negative plate. It won't literally fall. It's just going to travel, let's say, from left to right, but it will pick up speed as it goes. And so that means I'm releasing the potential energy that was there when it was sitting there at that plate. So remember, the first time what we did is we took the positive charge and we moved it from the negative plate over to the positive plate. That's kind of like lifting a rock. And now what we're doing here is we're releasing that rock and we're letting it fall back down. So now it's releasing potential energy. That's why it's negative 10 joules of electric potential energy. Let's do a couple more examples. I mean, if you got it at this point, you can just drop off the video. But for completeness, let's just do this. What happens if I take the negative charge and I bring it from point A at positive 5 volts down to point B at negative 5 volts? Again, we use the same sort of thing. And you got to be careful of what VB is and VA and, whether you're subtracting a negative, all that sort of stuff. So VB is at negative 5 volts. The place where it starts is positive 5 volts. So minus 5 is minus 10. It's a negative charge. So negative times a negative is positive. So when I move it from positive 5 down to negative 5, I'm actually increasing its electric potential energy. And the way to think about that is that the negative charge is very attracted to the positive plate. And so it's going to be hard for me to pull it off there, and it's going to be very hard for me to deliver it all the way down here to the negatively charged plate. So I have to do work to take a negative charge from positive 5 volts and bring it to minus 5 volts. That takes me a lot of work. And so when I put in that work, I basically establish 10 joules of potential energy in that charge when it's sitting at minus 5 volts. What happens if I make it go the other way? So now I've got it down at the minus 5 volt plate, and I want to move it up to the positive 5 volt plate, and it's a negative charge, okay? So we go through the whole thing, but we keep track of the signs, right? So it's a negative sign. And so now I say, okay, voltage at B is plus 5 volts, minus the voltage at A. The voltage at A is minus 5 volts. So 5 volts minus a negative 5 volts, that's a 10 positive volts, times minus 1 coulomb of charge, that's going to be 10 joules, negative. So I've lost potential energy. So again, you should think of it as this negative charge is sitting on this negative plate, and boy, it certainly wants to go up to this positive plate. So if you let it go, it's going to go that way, up like that. That's also like a rock falling, although this would be kind of like an anti-rock. If we had such a thing as an anti-rock, so things that responded negatively to gravity, so let's imagine I've got some tennis ball and it's a negatively gravitationally attracted ball, and I let it go, it's going to fall upward through the atmosphere. That's a little bit like what negative charges do in electricity and magnetism. If that helps, keep it. If it doesn't, totally forget it. So that's it. We've gone over in this video the difference between electric potential and electric potential energy with some simple examples, just moving a charge, a 1 coulomb charge, either positive or negative, between two plates. So I hope that was helpful. Feel free to leave comments below. Thank you.